But we're running out of time, so let's stop them and see if we can make some sense of what's going on. First of all, I asked your groups to make 3 conjectures. First of all, let's look at the one that we didn't have to argue about too much. The additive group mod n. So those of you that had to do the addition, we denote that group by z integers with a little subscript n on it. How many elements is in that group? N. That was because we never had to cross anything out in those tables, right? Everything already had an additive inverse. We already had the identity property. We already had the closure property. So there's n elements in the additive group z mod n. We'll talk about abelian. Let's talk about abelian real quickly now. Is this group always abelian, sometimes abelian, never abelian? Sometimes would mean it depends on n, right? So which is it? Always. Why is it always an abelian group? Because addition of integers is always commutative. And that's true whether you do addition modulo something or whether you just do addition in general. So always an abelian group, it has n elements. Okay. Is the multiplicative group mod n always, sometimes, or never abelian? Also always abelian because multiplication of integers is commutative. Absolutely. So at least, however scary this next part of the discussion is going to get, at least we're always talking about an abelian group, right? We have the commutative property, which is not something that we have in every group, right? But these 2 sets of groups, these 2 classes of groups, always enjoy the abelian, the commutative property. All right, so how many elements are in UN? So the ones that I gave you to work on with your teams were the cases n equals 5, 6, and 7, right? And so this was the piece of the pattern that you could observe just from the 3 examples in your groups. And so I heard some people coming up with some conjectures based on these 3 examples. What did you say? How would you fill in the blank about how many elements the multiplicative group mod n has? Well, okay, so but you started. Good, I broke you. Good. Then my job here is done. Well, some of you started, though, making a reasonable conjecture. If you're only looking at the 3 that are inside this box, what was the beginning of your conjecture? I think I heard every group say this.
Odd would just be -1.
Yeah, if n is odd, then just subtract 1, right? Because U5 had 4 elements, U7 had 6 elements. If you got outside this box a little bit and did U3, you would find out it has 2 elements, right? So that seems like a reasonable conjecture. But then what breaks that pattern? U9. If you look at U9, it only has 6 elements. It doesn't have 8. But Colleen observed that 9 is not prime like the others were. 3, 5, and 7 are prime. So, okay, so how would you modify that conjecture? If n is prime, then UN has how many elements? n minus 1 elements. Very nice. Okay, so tell me about how we might prove this. This would be a good place to wrap up this part of the conversation. And beyond the primes, let's not even worry about it for now because the pattern is very much less than obvious, right? Hang on to it. I want to hear it before we leave. So let's just see if we can come up with an argument for why this is true. What is the one element that we always have to throw away in these multiplicative groups? 0, because 0 always doesn't have a multiplicative inverse, right? So we know we're always throwing away 0. So n minus 1 is the most that we can possibly get elements. But why don't we have to take away everything else? What we're saying is that everything else has an inverse modulo n when n is prime, right? Which means, let's write this out. So for all x not equal to 0, maybe I'll say not equal to the equivalence class of 0, right? We should be able to solve x times y equals, what's the identity again? 1. We can solve this equation for y. And so how we would think about this, and again, this is equivalence mod n, is this turns out to be a problem in number theory. It's a very popular problem. Has anyone taken number theory? I feel like I've already asked you. What if I were to reframe this question as saying xy plus kn is equal to 1, What kinds of equations are those? Number theory veterans remember these? So these go by the fancy name of linear Diophantine equations.
Are we in math or science?
Yes.
Sounds like a chemical.
Linear Diophantine equation. And the point is, the linear Diophantine equation can be solved. We can find a solution for y here exactly when x and n have no common factors. Right? And so when n is prime, of course x is going to have no common factors with it. And so we can solve this equation. But yeah, that's a little crumb that comes out of number theory that can help to justify the claim that we made down here at the bottom. But in case you want to continue conjecturing, I'm going to leave this part at that. What was, Brian, your other thought on this?
If it's odd and not prime, it is n minus the greatest common divisor.
N minus the...
Yeah.
N minus the greatest... Well, not quite the greatest
Not the
common
greatest
divisor.
one,
But the...
Yeah.
How about this? N minus the number of common factors? Is that what you mean?
Oh, that's what I used.
Or something? Yeah, so somehow the answer to this question depends on common factors.